Good morning, everyone. I want to welcome you and thank you for joining us today for this discussion on CO2 utilisation. This webinar is part of the Royal Society of Chemistry's series discussing chemistry and climate change as we look forward to COP26, the United Nations Climate Change Conference in November. So for nearly 3 decades, the United Nations have been bringing together people from almost every country on the earth for global climate summits. And as you'd expect, the Royal Society of Chemistry will be showing how chemistry is vital for the understanding of tackling climate change through a series of online events. This event is being recorded and will be made available on the RSC website after the event, so you can find it at rsc.li/COP26. Today, we're bringing you some highlights of a Royal Society Faraday discussion on CO2 utilisation that was held virtually in April 2021. We're going to bring you a summary of that event, discussing how CO2 utilisation technologies could help in creating products that require carbon in a more sustainable way. So what is CO2 utilisation? Well, as we know, human activities create CO2. And although natural processes use CO2, we are creating more CO2 than can be used. And this leads to increasing levels of carbon dioxide in the atmosphere. One of the many possible solutions for is CO2 utilisation. Here, CO2 is captured and used to make carbon-based products that we need, instead of extracting more fossil carbon to make them. In a very simplest form, you can think of this as recycling CO2. So what can we make? Well, many carbon-based products can potentially be made from CO2. It's all a matter of chemistry. Construction materials such as mineral carbonates have a really large potential to use CO2 and permanently remove it, sequestering it in these carbonate materials that we can use for construction. Fuels also have the potential to use large amounts of CO2, but this would be a circular source of carbon removal, whereby this carbon can be used and then it would be emitted, and then if it could be recaptured from the air, it could be reused again to make that fuel again. Chemicals, polymers, and agricultural and food could also use modest amounts of CO2, again creating a circular carbon flow where that CO2 can be used again and again in the environment. So we've discussed the kind of products that could be made, but why would we want to do this? CO2 utilisation is not as simple as just looking to combat climate change, although obviously that's a big part of it. We want to remove CO2 emissions from the atmosphere. But we all need carbon-based products such as chemicals and polymers and building materials. And often these are made with new fossil carbon that's been dug out from the ground. So if we can widen our raw material base to include CO2, as well as biomass and other carbon sources, we remove that need to extract more fossil carbon, and we can recycle what's already above the Earth's surface. By making fuels, we can also help with the energy transition from renewable fuel. We need ways to store renewable electricity, and by making fuels and chemicals from CO2, we can create long-term storage options for that renewable energy. Another advantage of doing CO2 utilisation is we can repurpose other wastes by combining them with CO2 to create new products, creating a more sustainable and circular economy. So CO2 utilisation is an exciting emerging technology with many and vast opportunities. However, the success of CO2 utilisation will require new chemistries, new policy incentives, robust life cycle assessment to ensure CO2 reductions, new supply chains, and integration with carbon-free renewable energy systems. All of these aspects we discussed in the Faraday discussion, and we're going to bring them to you now. So first of all, I'd like to introduce the first panellist, Peter Styring, who is going to share some aspects of policy. Over to you, Peter.
Thank you, Katie. Let me just share my screen. Okay, hopefully you can all see that. Yeah, I see nodding heads. Good. So you've seen this slide already. I'm going to talk about chemicals and policy interventions. And this was a slide we put together in 2017 for Mission Innovation, which was the G20 plus the EU who met in Houston, Texas. And you can see the vast array of chemicals that you can make. And as Katy said, this is moving towards a circular rather than a linear economy. And just one thing that I'd like to flag up there is in 2017, we identified surfactants as being a possible solution. There were no surfactants made from CO2 at that stage. Earlier this year, Unilever announced that their first laundry capsules made from non-fossil carbon from CO2 utilization had been launched in China. So you can see that by addressing these things at the policy level as well as the chemical level, we can start to make progress very quickly, and speed is really of the essence. This is a bit more complex, so I thought as this was an RSC event, we needed some chemistry there, but this is just a small sample of the vast array of chemicals that you can make from CO2. And chemists have the ability to make the impossible happen. And basically, if you can see something with carbon in there, there will be a way of using CO2 to make it. Whether the policy supports that, whether the economics and the life cycle supports that, need to be discussed as well. But you can see some key chemicals in there, like alkanes and alkenes. Another one that really has taken off in recent years is the production of methanol and then dimethyl ether from the methanol that you produce, or even directly from CO2 to DME. And there have been examples of this being commercialized, and in particular Oberon Fuels in the States, who recently put together a joint venture with Suburban Propane. So this is really now starting to hit the market. But of course, there will be policy that's required to develop this technology, because this is, people think it's a new technology. Actually, it's been around for many years. Aspirin salicylic acid was in the late 1980s. Urea, for example, was around 1923. So CO2 utilization has been known, but we now need to readdress CO2 utilization in policy development. We're aiming to reach net zero, and we're looking at 2050 to do that as the UK, although the Prime Minister has recently said that electricity will be decarbonised by 2035. It's an ambition. We can discuss that. But also, I want to pick up a point there on decarbonisation. We are not looking at decarbonisation. That is a wrong term. We're looking at defossilization of industry and energy. It's the fossil carbon, the new fossil carbon that is released in a linear way to the atmosphere, which is the problem. If we can drive the U part of CCUS to be a circular approach, then we have a more efficient and more robust way of moving towards a transition to net zero. We have to remember that the S in CCUS is a linear component and that it's waste treatment, whereas the U is a value added component where we recycle the CO2 to make a commodity. So in this case, it's a feedstock and not a waste. It's a well-established technology, but there is still great potential for growth. So in terms of the chemistry, chemists are great. They can do this. We can do anything we like. In terms of policy, it becomes a little bit more tricky. So if you look at the CCUS policies, they tend to relate more to the S than they do to the U at the moment. So we need to follow that through and really develop it so that U is recognized as a key component. And when I say U, that does not include enhanced oil recovery, fizzy drinks, euthanizing chickens, as you've probably seen in the media in the last few weeks. There's a dichotomy. We see CO2 as a problem, but we also see it as an essential for the supply chain. If you don't have pure CO2 for the food industry, then we can start to get breaks. So we need to act before it's too late. And if there is a policy, that's great. If we have politics, it's not so good. So we need to follow the science and not follow the sheep. So we need to do evidence-based policy recommendations. The interventions that we need are multiple. They are fiscal, and that might be a carbon tax or changing VAT, for example. It's financial, so who invests in these products? And for a carbon capture technology that I'm working on at the moment, it's the company who's footing the bill for the capture unit. This is coming in from private sourcing. We need political interventions. We need politicians to realise that CO2 utilization is both a circular economic approach and is producing wealth for the country because the products will have value. There are social impacts as well. If we change one policy or one intervention, we might adversely affect another policy or intervention. We need case studies, and I've given you an example there of synthetic fuel. This is either synthetic aviation fuel, or it could be synthetic road transport fuel. But there is a series of different interventions that are needed, and we need to be careful that we don't get this wrong. It's like a domino, a row of dominoes. Once you start knocking one domino over, the rest might follow. And it has to be done in a positive way. And we also need public acceptance. The public needs to be aware of this, but they need to accept that this is for their good, it's for the good of the community, and it's for the good of society. So with that, I will hand back to Katy for the next presenter.
Thank you very much, Peter. Just to point out to all the participants today, please add any questions you've got in the Q&A box. We're going to be having a panel discussion at the end of this session. So anything as we go along that you'd like to ask a question about, please feel free to do that. So next, I'm going to invite Professor Rudiger Eichel to discuss with us how we can convert CO2 into fuels, into Power-to-X.
Yeah, so many thanks to Peter for setting the scene. So I'd like to talk about a particular approach, which we named Power-to-X, as an efficient flexibility and certainly emission reduction option. And as we have seen, we are following a race to zero. So what can we do in order to enable all industrial key sectors to contribute to our emission goals? So we have the energy sector, and this has been shown it's quite easy by a strategy of decarbonization, which means a transition of the energy system towards renewables. But we have key sectors which are not easy to electrify. And because we are doing chemistry, we cannot kick out the carbon. So we need carbon, but we need to think about alternative carbon sources. And this has been outlined by Peter already. So we need a strategy for a defossilization of industrial key sectors like chemical industry, like transportation and so on. And this is what we term Power-to-X. So this means feeding renewable energy into key sectors that cannot be directly electrified. So in order to do so, we need to develop novel technologies. We need to transform our thinking from a linear to a circular economy thinking. And here we do not only technologies like electrochemical water splitting by electrolysis, but we also need technologies for electrochemical CO2 activation. And here we develop novel technologies like CO2 electrolysis, or even the electrocatalytic synthesis of base chemicals or intermediates in terms of electrocatalysis. So electrochemistry, electrocatalysis is always the means and the lever in order to feed the renewables into the chemical sector. Now, if we want to do this at a big scale, we need to think about the economical meaningfulness of these technologies. And the good news is you can do it right if you think about a valorization strategy, which means, yes, there are products where you can find, or where you can come close to a positive business case. And this is shown here, which means if you think about an electrocatalytic production of base chemicals like formic acid, like propanol, ethanol, and so on and so forth, then you can do it at a positive business case. And so this is what we actually do. And one of the nice examples is shown in a big project that we have in Germany. It's termed the Copernicus project. And here we have one of the satellite projects. It's termed Reticus, where we produce green care products simply from air and water and from renewable electricity by adding all the steps we need to a complete power-to-X value chain, starting from CO2 electrolysis, using fermentation, and then ending up at a green care product. And so now this paves the way towards a roadmap. So to our opinion, the best strategy to start is to start with the markets where you have the highest valorization, to scale up the technologies in these markets, and then finally to end up to produce liquid circular fuels in terms of power to fuels. So this is by far the biggest market. So it has the ability of the highest CO2 reduction, but clearly it's the hardest markets because the valorization is quite small as compared to the chemistry sector. So in order to do so, we need lots of renewable electricity. So these are the numbers of Germany. And just to make a long story short, in Germany, we have the potential to produce about 800 terawatts of renewables. But for defossilization of all industrial key sectors, we would need approximately twice of that number. So therefore, we have to think in a global fashion, and we have to link countries with renewable sweet spots to countries with industrialization and where we need renewable products, power-to-X products. So the whole topic, to my opinion, is a topic of global interest and importance. And this has brought me to the end. I hope I could raise some questions with these initial remarks, and I give back to Katy.
Thank you for that interesting introduction to Power-to-X. Next, we're going to hear from Professor Colin Hills, who's going to talk about mineralization technologies.
Well, good morning to you all. There's been a bit of a change in focus in recent years from the sequestration of CO2 to utilization, from the S to the U, as Peter was saying a few minutes ago. And what we notice when looking in the literature is there's a bit of a lack of a reference point. So what we try to do in the work I'm going to present to you in a minute is to give an analogy with nature, and also give some understanding of the kind of amounts of CO2 that can be potentially mineralized in the UK, and how they relate to the CCUS lead reduction targets that have been published by the government. So I'm going to, if I can move my presentation on, there we go, going to move to my next slide, which is a much more simple representation of the one that Katy showed a few minutes ago. You know, in our natural system, CO2 from the atmosphere is used to weather rocks by nature. It is taken into the aqueous environment, into the terrestrial environment, where it's largely chemically and biologically mediated. What we want to do is to take it into a factory represented by this black box on the right-hand side there, where the CO2, which either comes from the atmosphere or from emissions, are mineralized, and our approach is using industrial process waste as the substrate to mineralize the CO2. Now, on the left-hand side of my high-tech chart here, you can see some things coming in from outer space. Now, interestingly, one of my students recently wrote an essay saying that Priestley invented carbonation in the 1700s. Well, I think Priestley was several billion years too late, actually, because we have evidence from outer space that CO2 reacts with minerals in space, because we find carbonates in meteorite type materials that have entered our atmosphere, being found on the ground. So I think we have good evidence here to say that carbonation is a very natural process that's been operating for an extremely long time. Now I'm going to show a little video which gives more of an introduction to what we're trying to do and our analogy with a natural system. I'm standing at the base of a low cliff not far from Dover in the southeast of England, and the cliff here is made of chalk. Chalk is composed of the skeletons of microfauna which grew during the Cretaceous, when there was a thermal maximum. In other words, there was a lot more CO2 in the atmosphere and the Earth was a lot warmer. You can argue this is Mother Nature's response to global warming at that time. And this chalk was laid down over 30 million years and is over 1,600 meters thick at its maximum, of which about 500 meters is exposed in the southeast of England. If we're going to address global warming through carbon dioxide utilization, we've got to do things in human timescales. We need to be looking at tricks that we can pull that take these processes that Mother Nature teaches us about and turns them into industrial processes that act more quickly. What I hold in front of you here is mineralized CO2. It's been mineralized on a waste-based matrix. It's hard, it's monolithic, it's suitable as a construction material. It's made in minutes, not millions of years. And if we can get our act together and we can industrialize these sorts of processes, then we have a good chance of mitigating gigatons of CO2 going into the atmosphere. So I hope that made sense. So really, our analogy is to try and find a link between the natural and system and managed mineralization, and that we can do this in timescales that allow us to develop industrial processes. So as I mentioned, our approach is to take waste as substrates that we can mineralize the CO2 upon, and there are many CO2 reactive wastes that are out there that are being produced on an annual basis in gigaton quantities. And we can think about not only directly mineralizing CO2 on these waste-based substrates, but also we can think about the indirect CO2 offsets that are produced from processing these waste arisings. And by comparing our CO2 with transport in nature, we can come to this analogy that gives us a bit of a reference point. So our approach then is to look at mineralization at ambient temperatures or mild temperatures and pressures, which are analogous with near surface conditions. However, we can assist carbonation at moderate temperatures and pressures as well. Of course, when we use processes of this type in an industrial application, we unfortunately put the price up because they tend to have an energy penalty, but they are analogous with subsurface environments. And here our reference point is the chalk in the southeast of England. There's about 1,500 cubic kilometers we calculate on the back of an envelope. And as I said, these were formed over 30 million years. So if we look at natural carbonates, we have active sequestration we've discussed in ocean, on land, and also into ultra basic rocks through weathering. And there's some quantities that are given there on an annual basis. But of course, the CO2 that enters the geosphere tends to be recycled largely by hydrothermal and magnetic processes, and it tends to stay there. And in fact, about greater than 99%, if I remember correctly, of the carbonate on our planet is within the geosphere. Now, in terms of human timescales and what we can do with accelerated mineralization, we think if we take, for example, 5 residues that are found, industrial residues that are found around the world that total about 4 gigatons, it's pretty straightforward to get into those, about half a gigaton of CO2 each year through direct mineralization, and indirectly a similar amount. And that's quite meaningful. This is in comparison with our example, which is the chalk of southeast of England, where about 0.4 megatons of CO2 was mineralized by these natural processes over this 30 million year period. So 0.4 megatons per year. Now, interestingly, our work was recently featured in 39 Ways to Save the Planet, this BBC Radio 4 program. And within that, there was an independent assessment of the potential of mineralization by the Royal Geographical Society. And they reckon there's potential to manage about 6% of CO2 emissions to the atmosphere through mineralization. So their calculations certainly compare with our own back of the envelope calculations. So what have we found that's missing then? Well, there's been a clear articulation of the technology, an understandable reference point, and we hope that we've started to address that. And we certainly need to avoid the black box approach. Although commercially this is driven, it is a real negative. We need people to understand what we're doing, and we need them to understand that our processes are not alien from those from nature. And in terms of the way forward, well, you know, we know that managed mineralization has potential for avoidance of gigatons. This is backed up by the Royal Geographical Society I mentioned a few minutes ago, and the literature. And in respect of our UK targets from the government's 10-point plan, we think in the process residues that are available in this country, about 60% of that target target emissions reduction could be met through mineralization. And I need to point out that we're not talking about theory, we're actually talking about real stuff. Mineralization is here in the UK, it's fully commercial. There are 3 fixed plants that are operating, and more recently a mobile plant-based system has been developed, and its first commercial deployment is for Vicat, the French national cement company in southern France. Thank you very much, and that's where I will end my presentation.
Thank you, Colin, for that very interesting introduction to mineralization. And our final speaker is Professor Andrea Ramirez, who's going to talk to us about how we can assess these technologies. Andrea, over to you.
Yeah, thank you, Katie. I'm just going to share my screen. Hopefully it's, do you see my screen? Assuming
yeah, that's great, thanks.
Yeah, perfect. So, hello, everyone. So I think we have now a big picture of what CO2 utilization can do. And if you have been following the debate, you know that you have kind of 2 teams, if you want to call it like that, like it's happening with most mitigation options. And in the case of CCUS, it has been looked, it has been assessed both as a solution by some and as a distraction by others on what we need to do to reach the climate mitigation targets. And when you look a little bit about what is causing this polarization, is the disagreement on what is the role, the benefits, and the bottlenecks. And these are typical examples of studies who are posing kind of different pictures. And I think what makes it very difficult for any person outside, but also for policymakers or decision makers on industry, is that you cannot compare the assessments one-to-one. So within their own boundaries, they take to have very valid points, but when you kind of put them together and see, does it make sense? You will see a big range on what can, for instance, CCU contribute to the climate targets, sometimes between 0.5 to 10%, and this is whether or not you are including things like enhanced oil recovery. There is a difference in the products that are included in such analysis. There is a difference on what you include in the analysis and what you leave out of the analysis, what we call the system boundaries, whether or not you are including the end-of-life emissions, where indirect effects are or not accounted in the results. What are you comparing it to? What are you displacing? What is the timeline of displacement? And how has CO2 evolved over time? And what will be, whether you are capturing or capture carbon depth in the case of bio CCO concepts, or even increased amount of CO2 take over from the atmosphere in some of the carbonation concepts. So I think it is inherent to the fact or to the strength of CCU that it produces a lot of products. So therefore, it's very difficult to just say, all of them together are the way to go. The assessment that we do from a life cycle point of view, but also from a cost point of view, tend to point out that it's very case related. So whether you analyze fuels, we'll get a different picture that you analyze food products, that you analyze basic chemicals or specialties and materials. And that is an answer that is unsatisfactory for a lot of policymakers. They would like you to get a yes or no, but I think from an LCA perspective, from a techno-economic perspective, we keep hammering about the conditions on the systems in which these technologies are implemented. So we cannot just make a big assessment. And the other thing, at my university, we are currently working a lot also on electrochemical conversion of CO2, which Colin was describing before. And these are typical assumptions that tend to be very confusing and create polarized opinions. And I think when we speak about going away from the black box and assuming realistic cases, it's because we want to actually help decision makers to implement these technologies in the right way and in the right setting. So therefore, we see a lot of the life cycle assessment either assuming that the CO2 is just at gate or is fully pure, but you don't see where it was purified from and what is the energy and the carbon footprint of purification and uptake. And that's saying there are some technologies that do not don't need to have CO2 capture itself, can deal with flue gases, which is an advantage, but only to take it within the system boundaries. And the price of the CO2, the carbon footprint of the CO2, or the fact that energy is being used in the process. And for the life cycle assessment tends to be say, well, you know, it's going to be available, it's going to be renewable, it's going to be cheap or for free, it's going to be continuous, even though it's intermittent, and it's not going to have almost a no carbon zero footprint. And I think a lot of the things we speak when we do LCA or techno-economic analysis is try to avoid free lunches, try to understand exactly what do we mean with that, you know, if it's really dedicated, intermittent, is the intermittency affecting the technology? And if so, can we already do something? Can be an advantage, can be a synergy, can we design technologies in a different way? And that is part of what I'm trying to show here work we are doing in process design in my group, trying to understand how can we design actually maybe more flexible chemical processes that we have today. But that flexibility when you design it, and this is an electrochemical conversion of CO2 to ethylene, comes at a cost somewhere. It's a trade-off. In this case, for this particular design, it's not always the case, but for this design, it came at a cost of a little bit reduced heat integration in order to increase the flexibility of the plant. We actually reduced the size. And the consequence, you also see between up and down that, you know, without needing to know what every equipment looks like, it's a less complex plant, but it has an impact on the layout, on the capacity, on the equipment, on your economics, and also in your energy and mass balances, and therefore in your life cycle assessment. So we try to move away from the black box and say, well, you can put a storage function before this and run this continuously, that the storage will have a cost and will have a carbon footprint, or we can try to design processes and make use of that flexibility, and that also comes with a trade-off, let's identify that. The other point that we want to, I would like to point out is in the whole, you know, field of things that need to happen, all the chemistry that needs to happen. Carbon accounting just looks like the most simple thing. How difficult could it be to account your carbons throughout the life cycle? But if you do it without understanding well the concepts and the methodologies that are using, it results in very strange conclusions where you have suddenly emissions of negative emissions, which I still don't know what does mean, or you have actually systems that are producing more CO2 than the reference, but you are calling negative, or you have actually avoidance and negativity at the same time, which is not properly communicated, and then policymakers may not see the benefits of the option. So yes, carbon accounting is relatively simple, but you need to understand what are the concepts and what are the methodologies, and we still need to solve some of the bottlenecks on accounting circularity, since most LCA has been designed for linear systems. And I think I already made this point. There is no unique answer to a question of economic or environmental performance of CCU in general, but we know at this point that there are a couple of highlights that we already see. One of them is the product and the time the CO2 is stored in the product matters. And the longer the CO2 is stored in the product, from a climate perspective, the much better. The market size matters for just to make impact and the need of impact. So the bigger, the better. And that's also why we are looking a lot at cement, aggregates, this kind of construction products. The source of the CO2 matters from an LCA point of view, whether it's CO2 from the air, whether it's fossil CO2, whether it's bio CO2. It matters, and it has implications for the life cycle assessment. The footprint of the energy, so electricity, heat, and hydrogen, determines at a large scale the footprint of the CCU products. So if you are going to have CO2 utilization products and you are just going to use fossil-based energy, it's not going to take us to a place where we need to be. So this kind of technologies highly rely on us having the energy and the hydrogen, which are low carbon footprint, which I think was a point made before by Colin. No free lunches. And anything that we account or we figure out from an LCA point of view, we have to see it from a technical point of view, from an economic point of view, and vice versa. We need to really understand what are we displacing, when are we displacing that product, are we adding instead of displacing, and how from a policy point of view can we steer the system in the right direction. And of course, a life cycle assessment is not only about CO2. So looking at what are the impacts or the benefits on water use, on land use, on critical raw materials is an important part of transforming what we have today to a more sustainable industry and society. So that's from my side.
Thank you very much, Andrea. Everybody's going to turn their camera back on and we're going to start a panel discussion. So if you've got some questions, please put them into the Q&A box and we'll hopefully try and answer them. But first of all, I'm going to start with a general question to everybody. We've talked a lot about different types of products from CO2. What do you think we're going to start seeing emerging onto the market first? I know there are some already out there, but what can people look to be seeing? What are they going to see in their shelves? What are they going to see that they could buy or purchase first?
Aggregates, cements, relatively chemically easier, long-term storage, commercially available by some companies already picking up, but also by the main industry, by the cement industry. So I think that will roll out relatively fast compared to others where we still need to do some technology breakthroughs.
So I showed already our sort of best practice example where we want to come up with a green care product. And this is anticipated to be on the market within latest 2 years. But this will be also a type of experiment because everything we produce from CO2 as a carbon feedstock needs more energy input to produce a chemical as compared to a fossil carbon source. So therefore, naturally, these products will be more expensive than their fossil counterparts. So therefore, we will have to learn how society, and this has been outlined already by Peter in the beginning. So we will have to learn how society accepts green products. Is there a willingness to pay a bit more for a green product as compared to a gray product? And most probably we will have to trace it back to our tax system. So how do we deal with CO2 taxes and so on and so forth? So therefore, this is a multi-dimensional and multidisciplinary example or experiment, to my opinion.
Yeah, just to add to that, I fully agree with Rudiger and Andrea. It has to be something that stirs the public interest. It's a marketing tool for one thing, but we shouldn't be greenwashing. Whatever we produce has to have a reasonable price, but also the same or better performance. We can't put a low quality product onto the market and then expect people to pay a premium. What do I think it'll be? I'll leave the construction materials to Colin because he's the expert on this. In terms of commodity products, I mentioned the Unilever laundry capsules in China. That may come over to the UK, who knows? But I would also point to things like dimethyl ether. So Ford in Aachen are heavily pursuing this. But also the winners of the Nova Institute Prize last year was a company called Airco in New York who make air vodka. So this is vodka made from CO2 and renewable hydrogen. But they also made hand sanitizer at the height of the pandemic. And that shows it can be done, and they gave that free to New York City hospitals. That shows it can be done at a reasonable price with the performance that's required. And, you know, they sent me a sample. They sent me the hand sanitizer and not the vodka.
Yeah, I was going to ask.
Yeah, I've got 3 bottles of hand sanitizer.
Me too.
It smells very nice. I've not drunk it. But it really hit the market at the right time. So there are lots of things that will hit the market.
Can I add something before just Colin and go into the construction? I think there is another thing that I think is going to pick up, Syngas. So going to CO2 to CO. It's not a product for the final market, but it could be a big chemical building block for the industrial sector. And going to CO2 to CO is relatively, you know, in the thermodynamic scale, I think we can already do that. So I expect Syngas also to pick up as an intermediate. So not only in the final stage, but also producing intermediate chemicals will be important.
Colin?
Well, the thought of an air vodka that's shaken rather than stirred is quite intriguing. I think in terms of construction, there's somewhere in the region of 20 companies that are in this space at the moment at various stages of development. And we can think about CO2 being stored in limestone-like materials in the built environment. I mean, there's nothing particularly controversial about that, and it's easy to understand. And if we think about the actual storage element itself, i.e. the CO2 is mineralized and sequestrated, it can stay in the built environment for a very long time, not just for the service life of the particular structure that takes these materials, but also in being recycled thereafter, as most construction materials are. So if we think about putting limestone construction products out there and that they last a long time, I think we can see these being readily accepted by the public. I mean, it's easy to relate to, and that's part of the challenge we have. It's public acceptance. But thinking of it from a commercial point of view, most people that buy materials want a cheap one. They want one that performs, and they'd prefer to have yours cheaper than the traditional material. So there's a lot of pressure on keeping the costs low.
Thank you. And we've got a question from the audience. So the question is, how would you get governments and the general public to prioritise defossilisation over other renewable energy and policy issues? So we'll start with Peter, because he started on policy.
Yeah, so this is the no silver bullet approach. To do CO2 utilization, you will need energy, and you will need defossilized energy. So you cannot consider really using conventional energy sources to try and defossilize an industry, because you're just shifting the goalposts. So I think it's a tandem process. It's the domino effect, if you like. As soon as you say we're not going to prioritize low carbon energy or electricity, then you automatically have an effect on the CO2 utilization market. So it has to be seen as a parallel process, that you show the importance of different energy sources for different applications. And if I take transport as the example, if I was to, and I don't want to promote any vehicle in particular, but if I was to drive a Renault Zoe fully electric, that would be much better than driving a VW Golf diesel. But if I was to drive an SUV electric or a high performance electric or one of the many executive electrics you see on the market, I'd be better driving the VW diesel because of the embodied life cycle emissions that are associated with that. And it's going to be a case of supply chain as well, because we're assuming that renewable energy will be 100%, or renewable electricity will be 100% of the market in the UK by 2035, if you believe this recent statement. How realistic is that? There will be demand from every possible source for that energy. And as you transition from the normal use of electricity to the use of electric vehicles, you're putting the demand side up considerably. So it's not a simple effect, and you need to look at the social aspects as well, making sure you're not creating social underclasses in transport and in fuel.
Rudiger, can we get your comments on this as well? Because obviously in your slides you showed the vast amount of renewable energy that would be required just in a German context to make fuels from CO2, and you mentioned that Germany wouldn't have that capacity to actually meet that target. So how do you ensure that the right amount of renewable energy, because we're going to need renewable energy for so many different things of our lives going forwards, how do we ensure that we're not taking the energy from one place and putting it into another place, and we're using the renewable energy to the best that we can?
Yeah, so this is I would say this is not an easy question to answer, but we need to find a solution to this. So I put it in a global context. So let's say we have, or if we are thinking from the power to X value chain, so we have an upstream and we have a downstream process, and most probably, to my opinion, the upstream process will be somewhere in the world where you have lots of wind and lots of sun. And then you will produce energy in a chemical somehow that you can easy and safely transport. So to my opinion, this will not be pressurized hydrogen, but it will be a chemical hydrogen carrier. So this might be methanol, this might be formic acid, this might be any other type of liquid organic hydrogen carrier, LOHC. The advantage is if we are managing to build up such a global power to X supply logistics, then we can not only transport energy in form of a chemical, but we also can transport hydrogen, and we can transport a green CO carrier, which means we can transport it to any place of the world where we have the downstream chemistry. And this will be, to my opinion, the key to achieve our ambitious climate goals. So therefore, we have to think globally, and we have to think about logistics. So it's not only the value chain itself, but it has to be at some place how we can manage to ramp up the according logistics.
Thank you. So, Andrea, you talked about assessment and the complexities and a bit about what we could call greenwashing. How, as a consumer, we see lots of claims out there about things that are carbon negative or going to net zero. How should we be approaching those kind of claims, and what can be done within the assessment community to make sure that everything is on the same kind of standard level playing field?
Yeah, that's one that we have been dealing with for as long as standards and life cycle assessment has been around. I think sometimes what it seems to be the most logical things to do are somehow the most difficult to be implemented. So we have discussed a lot about transparency. How transparent can we make the assessments? And of course, you can have transparency, but you need to have the other side that is able to understand the data that you are giving them. I think in the Netherlands, we are at this moment discussing the possibility, not only in the Netherlands, in other places, of having material passports. as for instance, a means to try to do that, to try to do to increase transparency, to give enough data of where the carbon flows. If, for instance, the system that Colin is proposing will take place, we will have carbon going back and forward, but we will have local policy incentives. So how do you manage the local policy incentives with the flows of carbon going around? You will need to make use of artificial intelligence, chain block analysis, material passports to make certain that suddenly flows of carbon are just not appearing or disappearing in the system, but we are still seeing an increase in CO2 emissions temperature global-wide. So I think this is such a big challenge. It's a logistic challenge, an institutional challenge. And we need to start somewhere. We need to start small. We need to start with a company who actually is able to control a little bit the value chain and show how can it be done. And maybe a second will follow and a third will follow. This is it's also partly going to be a bottom-up initiative of a lot of multinationals as well, who need to show that it's possible because they have a little bit more information and data than the general public, so the governments also can, have best practice. It is going to be also driven by the willingness of companies to be more transparent about their footprint.
Thank you. We want to talk a bit more about policy and governments. And Colin, you showed us a block that has been made and can be made in the construction material. Oh, you've got it there. You can wave it.
This one.
So what's preventing that reaching mass markets, the growth in that? Is it policy related? Is it incentive related, or is it technology related?
That's a very interesting question. Before I answer it, I'd like to say two things, building on what's just been discussed. Through CO2 Chem, we've talked for some time now about labeling goods with their carbon footprint. This would give the consumer the choice. So one very important policy initiative might be that we agree a methodology to enable all products to be labeled very clearly of how much carbon has been, released, used in their production. And then you can compare then apples with pears, and you compare like-minded products as well, and you can make an informed choice. And I think that could be a very important step for the general public, and it would also incentivize industry as well. From the construction materials point of view, I had my eyes opened a couple of weeks ago when I visited a new factory in East Anglia that was producing cement-based construction products. The plant was using renewable energy, and all their vehicles were electric. That is, those around the plant for moving materials about in the stockyard and within the factory space. And they showed me their electricity bill, their energy bills for the previous month, and it was less than £2,000 for a whole factory unit operating, making construction products. And that was really quite something. And what it says is this company had built this plant fairly recently. All the lighting was LED, for example. Their choice was to build a low carbon factory as they saw it. Now, clearly the materials that they were processing and turning into construction products contain cements that have a high amount of carbon associated with their production. But there are alternatives coming along. And so if you couple those two together, then you're moving in the direction of having not much energy being expended when you're making the product from raw material feedstock that has a relatively low carbon footprint as well, to put it crudely. And that's really exciting. You can see, we're starting to see these things happening now. Now you have to tell me what your original question was, because it's gone over my head.
I said, what was the barrier from your mineralized product reaching market? Is it policy? Is it technology?
It's very much price. As I alluded to earlier on, specifies buyers want a product which has benefits, but at the same price or lesser price. And we've got to break that barrier, if not only initially, in the longer term as well, where people are prepared to pay a couple of pence per brick extra or whatever to get a low carbon product out there. And again, I think that might be, there's potential to drive that from the consumer, because if the consumer knows that these bricks A contain so much carbon and bricks B contain so much carbon, and in this case less, they might be prepared to pay those few pence difference. And you know, the bottom often informs the top.
So Peter, would you like to comment on any policy incentives that you think should be stated from a COP perspective? We're talking about global policy and global moving towards reducing CO2 emissions. What message would CO2 utilisation, I suppose, want to take to something like COP?
I think Colin's comment about the labelling is very important. That we need a metric by which people can judge the effectiveness or the environmental credentials of the product. Otherwise, we have the Wizard of Oz effect, where we have the Wizard of Oz behind the green curtain, putting lots of policies out with no real science behind them. I've got a brilliant cartoon which I need to edit because I don't show it at the moment, that my daughter did for my birthday with the Wizard of Oz. It's really getting that message across that we have to do something, and that we have to do it now. And the comment about the factory, I'm just working with a company at the moment who's making our new carbon capture unit. They are now carbon negative in their factory, and it's a scope 3 analysis. I've seen the data. It's real. They are really doing something. And it's companies like that that will lead the way. Hopefully in the next couple of weeks I can tell you who that company is when our trailer comes with a big carbon capture unit on the back of it. But it's really that the government needs to think of all the aspects of a policy, that we don't work in isolation. And the work we did for Bankers for Net Zero and the APPG on fairer business banking, the model we proposed was academics working with industry, working with policymakers, but the glue that holds everything together is the financial sector. And I think that's the way we need to approach things. This is everyone pulling together. And as I said the other day, our ambition now is to make Greta smile.
And with that comment, we've reached the end of our hour together. I want to thank all our panelists for joining me today to discuss CO2 utilisation. As you can grasp, CO2 utilisation is an exciting and quite complex topic, but has great potential for impacting climate change, for making us products using lower carbon. And we're excited to see what happens in the future within CO2 utilisation. So I want to thank you all for joining us. And if you're really interested, you can watch this again, as we said, live on the RSC website. Thank you very much for joining us.
The chemical sciences are at the heart of sustainability solutions. Sustainability, powered by chemistry.